Hi, welcome to part 2 of the polyfolding tutorial. Last time we left off with the build system node. We created a metric for all these primitives to be able to find parents for each individual primitive and form parent-child relationships. And then we created a matrix, a system basically, that used the edge between a primitive and its parent as the origin, or the midpoint of the edge as the origin, and 3 rotation vectors that were created from the directions of the edges. So basically we had a system that defined each individual primitive as an object. To create this system, we needed the connectivity information, so we kept the entire object a polygonal mesh. But now we want to use the information to transform the individual primitives, so we somehow have to separate all these primitives. If we turn on point numbers, you see that at the moment all these primitives are sharing their points. So for example, this point 3719 here is shared by all of these 6 primitives. What we need is primitives with unique points. So the points should be duplicated such that each primitive has its own set of points that are not shared with any other primitives. Then we can transform each individual primitive. Fortunately, we have a SOP that does this. It's called facet. So lay down a facet SOP and append it here. Make it visible and check unique points. As soon as you do this, you see that you now have a lot of overlapping points and all the Phong shading is gone because we don't have any connectivity in this mesh anymore. We can check this if we quickly append a point jitter to move the points around. And if you go down with the scale quite a bit, turn off point numbers, you see now we have individual primitives. That is good. Okay, so now how do we transform these primitives? The idea here is that we want to localize the primitives. That means we want to express the points in local space. At the moment all the points are still defined with respect to the origin of the world, although we created a system for them. Now we have to define them with respect to this system. That means we will move all the points of each primitive such that they are defined with their particular origin in mind. And if we have that, we can then use a different set of matrices to move them wherever we want. And that is exactly how chains of objects on scene level behave. So let's do that. Let's create another wrangle and append it. This time we want to use a point wrangle. Of course we want to localize the primitives, but what we have to move is the points, as primitives cannot be moved directly. So call this localize primitives, although it is a point wrangle. But before we attach it here, we want to promote the Xform attribute that is currently defined on prim level to points, just to make our life a little easier. So lay down an attribute promote, append it after the facet, call it promote Xform, and let's promote the attribute Xform from primitives to points, like so. And now attach the localize primitives wrangle. And let's press Alt-E to open the editor, and let's implement this. So let's create a matrix called Xform, and let's just import our Xform attribute for add Xform. Because we promoted the attribute to point level, we now can use the add syntax here inside of the point wrangle to read it. And now we want to invert the matrix, because we want to apply the inverted transform that the matrix Xform defines to all the points, to move them to local space. So let's create a new matrix, Xform inv, inverted, and let's use the invert function, like so, and let's invert Xform, like so. Now we have a matrix that does exactly the opposite of the Xform matrix. And now we can multiply all the points at P times equals Xform inverse. So we can multiply all the points by this inverted matrix. And as soon as we do this, we get this here. We get all the primitives moved to their particular origin and rotated accordingly. And that is why you see that these primitives are all aligned with one of their edges, and that is the edge that connected them to their parent primitive before. And they are all moved to the origin. With the primitives in this state, we now can build new matrices to transform these primitives back to the place where they have been, and then we can alter these matrices to make them rotate. The Xform matrix is the global matrix for the so-called objects. I call the primitives objects for now. And if we would apply just the Xform again, they would move to their old location, but we wouldn't gain anything from this. Instead, we want to move them to their old location by a different set of matrices. We want to express the transformation matrix with respect to the parent transformation matrix. And then we want to create a chain of matrices that are transformed one after the next, always with respect to the parent. And then we will finally reach the location where the primitives have been. But then each individual primitive is defined with respect to its parent, or the system of its parent. And that means if the parent transforms, all the children will transform with the parent. And that is exactly the behavior we need for the curling effect. So the next step is to localize the Xform matrices. So create a new primitive wrangle and append it. And call this one Localize matrices. Like so. Make it visible, and let's open the editor for this one. So to express each matrix in its parent system, we have to multiply the matrix with the inverse of the parent matrix. So let's create a new matrix variable, matrix, and let's call this par for parent, Xform for Xform, inv, inverted. And this will be the invert function again, because we want to invert the matrix, and then we use the prim function to find the matrix. Prim 0, the attribute to read is Xform. And then as an index we use I at parent, like so. So this is quite a mouthful. What happens here is that the prim function will read the matrix Xform from the parent primitive. That is still saved to all the primitives, although they are transformed to the origin. And then this matrix will get inverted. And now we want to localize each matrix, each Xform matrix. So we will create a new attribute called for@, for a new 4x4 matrix called local Xform, expressed in parent space. And that will be just the Xform, so the global Xform, for@Xform, that we still have. And now we multiply this by par Xform inverted, like so. Apply and accept. After this step, we have a new matrix that is called local Xform. Do we? Not on the points, but on the primitives. Actually, we don't have a matrix. We don't have a local Xform, and we don't have an Xform. And that is due to a stupid mistake I made. While promoting, I missed to check delete original off. This will delete the Xform attribute from the prim level. And then, of course, we don't have an Xform anymore, and we cannot create a local Xform from it. As soon as I uncheck this, I have Xform here, and I still don't have local Xform, and that is due to a typo here. So Xform inv is how we called the matrix, and if we do that, hopefully, finally we get local Xform. So now we have Xform here, and we have local Xform. And this local Xform is a transformation matrix expressed in the parent space, so in the space of the parent primitive. But we have to be careful again, because we have primitives without a parent, the root primitives. And we again have to correct for the root primitives, because this operation will not yield usable results if there is no parent matrix. So let's correct the border case again. Correct border case. And let's say if I at parent is smaller than 0, so whenever it is -1, in this case, let's create the local Xform for at local Xform, and let's make it just the global Xform. Because in the case of the root primitive, the global Xform is what we can use, because there is no parent. Okay, now that we have that, we correct it for the border case. So now finally we created local matrices from the global matrices. We have a matrix that defines the object in parent space for each individual primitive. And now we want to multiply all these local matrices together to create global matrices again. But this time, these global matrices will be composed of a long chain of linear transformations. We will start with the root primitive, and then we will apply one local matrix after the next until we reach the primitive. So the primitives will move to exactly the same location that they've been before, but not by just using one matrix, but by using a set of matrices, a chain of matrices applied one after the next. So what we actually did was decomposing the original Xform to a lot of successively applied local Xforms. So great, but to be able to move these primitives back, we need, again, one matrix that we can apply. So let's create this matrix by gathering all the parent matrices for each individual primitive and multiplying them all together. So create another primitive wrangle, and let's call it local to new global, like so. Type is primitive, press Alt-E. Okay, to be able to find all the parent local matrices, we first need the parents. So let's create an array parents, brackets to indicate this is an array, and then let's read I brackets at parents, which is the attributes storing the parent array. But be careful, we reversed this array to get rid of the -1s before, so we have to reverse it back here, reverse. And I know that there are more elegant ways of doing this than first reversing it, then removing one index and then reversing it back. Somebody pointed out in the comments to the first part of this tutorial that pop might do the trick. But I did it in my demo file like this, so I stick to it for now. It's not very elegant, I understand this. Nevertheless, after this operation, we have our original parent array back. And now we need the global matrix, so matrix, global matrix. This global matrix will be the matrix that is transforming the points back to their original location, but it will be composed of a chain of individual matrices. So let's initialize this variable with the local Xform for at local Xform. That is the very first matrix we use. And then we need the parent matrix, parent matrix, like so. And just initialize it to be the identity with the ident function. This gives a matrix that does nothing. And now we do it for each loop and go over all the parents that we have. So for each integer parent inside of the array parents, like so. And now let's multiply all the matrices together. The first step is to find the parent matrix. So at the moment it's the identity, we have to write something useful to this variable. So let's say parent matrix is prim, and then 0 local Xform, but of index parent. This gives the local Xform of the parent. And now the global matrix is multiplied times equals the parent matrix. This line says, take the global matrix, whatever it is, multiply it by the parent matrix, and then save it to the variable global matrix again. So these two lines inside of the loop will multiply each and every parent matrix on top of the other matrices until a root primitive is reached. So after this loop, we have a new global matrix. And we want to write it back as an attribute, but only if this is not a root primitive again, because a root primitive should just use the global matrix. So let's create an if statement. If I add parent, and this time we say it's bigger than -1, because we want the code block only to be executed if this is not a root primitive, brackets. And here we say for add local Xform is global matrix, like so. And this is again a little distracting, because I am reusing the attribute local Xform. It would be a lot clearer if I would create a new attribute, but then we would save the third 16 float matrix as an attribute, and this costs a lot of memory, so that's why I'm just reusing local Xform here, although it's not storing the local Xform anymore after this step. Let's see if we have errors. Press apply, and we have an error. And the error is here, parent matrix is prim not 0. Accept. Okay, now after this step, the attribute local Xform stores, in fact, a global Xform again. But this global Xform is composed of all the local Xforms. And that means that we later can go in here, in between here, and do something to the local Xform before it gets multiplied together again. And that means we can influence these local Xforms, and we can rotate or scale the individual primitives before they get transformed back to their location. The next step is to actually use this newly created matrix to transform our primitives back to their original location. So another wrangle, this time a point wrangle again, as we intend to transform the points. Point wrangle, like so. And let's call this wrangle Xform points. And let's append it and make it visible. Now, inside of this wrangle, press Alt-E to open the editor. And inside of this wrangle, let's first get the primitive that holds the local Xform. Because we are on point level here, it's a point wrangle. And that means to read the attribute local Xform that we created on primitive level, we first have to find the primitive the point is attached to. So let's say int myPrim. And this will be an array, as I intend to use the function pointprims, which gives all the primitives attached to a point, round brackets, and the geometry stream is 0, and we want to find the primitive for the currently processed point, so pt num, like so. And this gives all the primitives the point is attached to. But as we unique the points, this is only one primitive. So we just can use the very first index of this array. And now let's create the matrix variable called local Xform. And let's read with the prim function of stream 0. The attribute is called local Xform, like so. And now we just use myPrim and then index 0 as the index. And that is the very first primitive the point is attached to. So this will work. Now this gives the local Xform of the primitive the point is attached to. And now we can just write at p, again, times equals, so we multiply the point by the matrix and then store it back to the point. And we want to multiply it by local Xform, like so. And if we don't have errors, you see it works, we get our object back. So a lot of work for nothing. We started with this object, and after all these wrangles with all of this code, we have exactly the same result, but with a very important difference. And that important difference is that these locations are now reached by a chain of matrix multiplications. And that means we can implement something in between here to alter these transformations. Okay, now the fun starts. We finally are able to do something with our setup. And for this, you guessed it, we need another wrangle, a primitive wrangle. Primitive wrangle, and let's call this rotate. And because it's so important, maybe just color it red or something. And put it here in between localize matrices and local to new global, because we want to change the matrices before we combine them to form new global matrices, like so. Open the editor and let's finally implement the rotation code. So the very first thing we'll need is just an angle, and let's create a parameter for this. So float angle will be channel, let's call it angle, like so. And to make it more user-friendly, include all of this in brackets, and let's use the radians function on it. That means that the input can be in degrees, easier to read. Press apply, and if you now go to this little button here in the parameters window, the angle will be created. Maybe to be able to change it in the right parameter range, go to Edit Parameter Interface and change the range of our newly created angle parameter from -360 to 360. So apply and accept. Now we can input the whole angle range. And now we want to rotate the local Xforms. And we can do this by using a rotation matrix. So let's create a rotation matrix. So another matrix called rotmat. And let's initialize it to be the identity again, ident, like so. And now let's use the rotate function, which rotates a matrix by an angle and an axis. And let's rotate the matrix rotmat. It should be rotated by angle. And the axis to use should be the x-axis. So just give it a vector here. Can be a static vector, 1, 0, 0, which is the x-axis, like so. So this will actually create or set up a rotation matrix that does a rotation around this axis by this angle. And now we can apply this rotation matrix. But again, we only want to apply it if we are not dealing with a root primitive. So, same code as before. If I add parent is bigger than -1, only then do stuff. And the stuff to do is, let's alter the local Xform. So for add local Xform, and this should be the rotation matrix times the old for add local Xform. And we want to multiply this matrix from the left. That is why I write it like this. So let's press apply and let's see if we have errors. And if we don't have errors, now by altering the angle, you see it's working. All the strips are curling up. And they are very sensitive to the angle because the angle is applied to each individual primitive. So let's decrease this angle in smaller increments, like so. And you can see what happens here is that now these strips are curling, actually. So what's happened is that all transformation matrices that are all defined in parent space get this rotation of, at the moment, 4.77 degrees, or minus 4.77 degrees. And all of these rotations add up to form this curl. So it starts with the root primitives and then it curls up because each individual primitive is rotated inside of its parent system. And this gives this nice curly behavior. And you easily can imagine that this setup is very powerful because now we have control over the entire transform of each individual primitive, and not only that, of hierarchical strips of primitives. So we can apply transformations to entire strips of primitives. So now the effect is working, but we of course don't want to apply the same angle to all of the primitives. We want to animate the effect, and that means only applying the angle to the primitives that are currently growing. So let's introduce another node to animate the effect. And for this I will use a VOP. Primitive VOP. Let's call it Animate. And let's color it red too, to indicate that this is correlated with the rotate node. And let's dive inside. Okay, so the idea is that I want to use the distance attribute we created at the very, very beginning of the tutorial to drive the animation. I want to remap this distance between 0 and 1, but only use a certain range of it. If you remember here, we had this attribute that is a gradient, an attribute gradient over the entire object. And now I want to just take a certain range of it, say between 0.1 and 0.2, and remap it to 0 to 1, to use it as an animation parameter. So, inside of the VOP, let's first bind the dist attribute. Dist. Here we have it. And now we need a fit range. Because this distance here has a distinct range, but we only want to use a subrange. And which subrange is that? Well, let's define it by using parameters. First, create a parameter node. And let's call it position, to indicate that this is a position in the attribute gradient. And then let's create a second parameter, and let's call this one width, because that is the width of the area that should be transformed to 0 to 1. So now let's connect the position to the source minimum. So this number here will be the value that will be 0 after the fit. And everything that is less than this number will be 0 too, because this fit is clamped. And for the source max, let's use an add. And let's add the width to the position, like so. And now use this as the source max. That means the position plus the width value will determine the value on the attribute gradient that will be 1 after this operation. And everything that is bigger than this value will be 1 as the fit is clamped. So now we have our animate value. Time to bind it. Bind export and call this attribute animate, like so. Okay. Now let's go up one level and let's dial in the width of, say, 0.3. And let's see what this gives if we go to the geometry spreadsheet and to primitives and say view, hide all attributes, and then animate. We see that we at the moment have a value of 0.875 here. And if we change this, you see it is working. Maybe we can even try to visualize it. So lay down a visualizer. And let's visualize. Now, of course, we have to do this later in the chain, otherwise nothing will be visualized. And let's visualize animate. Here it is. for now deactivate the rotate and see what happens here. You see, this animation thing will happily move over the object. Can go bigger than 1, and then it will move entirely over the object. Great! This can be used to drive the rotation effect. So let's get rid of the visualizer and reactivate the rotate. But to use this value, we have to alter the code of the rotate. Because at the moment, only the angle is determining how much each primitive should rotate with respect to its parent. But by adding one line of code, we can change that behavior. Here we read the angle from the parameter. And now after that, let's write angle times equals add animate, like so. Because that means please take the angle that comes in from the channel, but then multiply it by the animate attribute and store it back to angle. And if we do this, apply and accept, we now have animation control. But it does strange things, and that is due to the fact that the values are inverted. At the moment, all the primitives get the rotation angle set. So let's revisit the warp and just change the destination min and the destination max. So we want a 1 here and a 0 here, like so. And now all the primitives get a value of 0, but only the ones where the animated value is 0, they get a value. And now we just animate this value back. And you see, it is now working. It curls up and then it closes the object. And I think this is pretty neat. A pretty neat effect. So this concludes this long and complicated tutorial. Of course, you can extend this effect by any means. You could go to the rotate wrangle and add scaling here. So create a second animation value that scales the primitive, and then create a scale matrix here and multiply it with the transforms. So you pretty much can do whatever you like with the transforms of the individual primitives. So basically what we created is the same thing as in rigging, where we have chains of bones that are transformed in parent object space. We have chains of primitives that behave like bone chains. And so we can make them curl, we can make them scale, we can basically make them do whatever we want. So thank you a lot for listening. It was fun to do this. I hope you learned a lot. Thanks again, and see you next time.
And now it's time to really thank all our patrons, especially PU Online Learning, Important Looking Pirates, Kyoko Sakane, Derek A. Johnson, Nick, Chris Ever, Rafik Anadol, Rob Bryant Jr., and Mohammed Al-Abri. Thank you so much for your continued support. Without you, this all wouldn't be possible. Thanks.